Chernoff and Jensen closed the chapter on bounds, and with it, the single variable story. But measurements come in pairs. A signal and its noise, a position in 2 coordinates, and they live on a continuum. This chapter describes 2 continuous random variables together. In this video, we meet the joint CDF, one function on the plane that records the probability of a whole quadrant, then differentiate it twice into a density surface where probability becomes volume over a region. Recover each variable's own density by integrating the other away, and run the machine on a flat disk and on 2 Gaussians, where a famous distribution falls out. 2 random variables, 1 experiment. Chapter 7 described a discrete pair with a joint PMF, a table of masses. On a continuum, single points carry no mass, so we lean on the tool that carried single variables across this bridge. Accumulate. The joint cumulative distribution function of x and y is the probability that x is at most x, and at the same time y is at most y. Keeping in mind that x and y are functions on one sample space, this is the probability of the set of outcomes where both coordinates come in under their thresholds. Picture it on the plane. Fix a corner point. The event collects every outcome landing at or below it and at or to its left, the whole southwest quadrant. Slide the corner up and to the right, and the function accumulates probability, the one variable sweep upgraded to 2 dimensions. Limits recover the pieces. Push y to infinity, the constraint on y evaporates, the quadrant grows into a half plane, and the joint CDF becomes the marginal CDF of x alone. Push x to infinity instead, and the marginal CDF of y comes out. And push either argument down to minus infinity. The quadrant slides off the plane, and the function falls to 0. The 2-variable version of the CDF endpoints we met for a single variable. One function carries both variables, and both marginals live inside it as limits. For a single variable, one derivative turned the CDF into a density. Here there are 2 directions, so differentiate twice, once in x, once in y. When the joint CDF is totally differentiable, this mixed partial derivative is the joint probability density function, and the order of differentiation does not matter. When the density exists, we call the pair jointly continuous. Calculus runs backwards too. Integrating the density over the quadrant rebuilds the CDF. And the density behaves as a density should, never negative and integrating to 1 over the whole plane. Now the picture to keep. When we built the joint PMF table, it stacked a lump of mass on each cell. Let the cells shrink and multiply, and the table melts into a surface, a height above every point of the plane, tall where the pair is likely, flat where it is not. And probability becomes volume. The probability that the pair lands in a region S is the double integral of the density over S, the volume trapped under the surface directly above the region. When S is a rectangle, the volume is the familiar iterated integral, x from a to b, y from c to d. One variable at a time again. The joint object answers every question, but often we want one variable's own distribution. In the discrete chapter, marginalizing meant summing a table's row. Here the row is a slice of the surface. Fix a value of y and cut the surface along it. The slice's profile shows how the mass along that line is spread across x. Integrate the slice over all of x, and the total is the marginal density of y at that value. The row sum from the discrete joint table video has become an integral. The marginal density of y is the integral over x of the joint density. No new principle here, just the discrete recipe with the sum promoted to an integral. Symmetrically, integrating out y leaves the marginal density of x. And the old warning carries over word for word. The joint determines the marginals, but not conversely. Just as 2 different tables shared identical margins, 2 different surfaces can cast identical shadows. Time to run the machine twice. First, the flattest surface there is. Let the pair be uniform on the unit circle. The density is 1 over pi inside the disk and 0 outside. Constant height, total volume 1. What is the probability of landing within radius 1/2? Volume above the small disk, a constant height times its area. The small disk holds 1/4 of the area, so the probability is 1/4. Under a flat density, probability is literally area. Now a curved surface. Take 2 independent zero-mean Gaussians with the same variance sigma squared. Their joint density is the bell curve spun into a two-dimensional Gaussian density, tallest at the origin, falling with the squared distance from it. Ask for the probability that the point lands within distance s of the origin. Switch the double integral to polar coordinates and it collapses, leaving 1 minus e to the minus s squared over 2 sigma squared. Look at what that is, the CDF of the distance r itself. Differentiate once, and r has the Rayleigh density, s over sigma squared, times e to the minus s squared over 2 sigma squared. The Rayleigh entered the course as a catalog entry. The joint density just derived it. The key idea of this video: one joint CDF carries a pair of continuous variables, differentiate it twice, and probability becomes volume under a density surface.